All right. One more thing about black holes. Let's do a specific example. How small does the Earth need to be? This is a semi-classical derivation. And so I'll talk about vaguely about where it's actually different from sort of more modern theories. But let's start out with, I have an object that's orbiting a black hole. And so that is M sub S. There's a sub S there for satellite, and I'm going to use B later for black hole. Now, if I do a force diagram, I just look, basically I've got a gravitational force between these two objects. So I've got my massive satellite, I've got my black hole, they're both pulling towards each other with some gravitational pull. I'm assuming the black hole is significantly larger than the satellite, and so I'm assuming that the effect of the force of gravity on the black hole is minimal, sort of like the Sun-Earth relationship. Now, given that force diagram right there, what I now want to do is concentrate on just the satellite. I have one force acting on it, and so I'm going to plug into F equals ma. So if I plug into F equals ma, well, the force is the force of gravity, and then the mass is the mass of the satellite times the acceleration, v squared over r. The force is towards the center. It is a centripetal force, therefore it's centripetal acceleration. I'm assuming a circular orbit, and so that v squared over r comes from that's the formula for centripetal acceleration. Taking the next step is I now put in this force of gravity right here. That this is the formula. So I have the gravitational constant times the mass of the black hole times the mass of the satellite divided by the distance between the black hole and the satellite squared. And that's equal to the mass of the satellite. That's from this mass right up here, times the speed of the satellite squared over the radius of the distance between the black hole and the satellite. If it's traveling in a circular orbit, then the radius of that orbit is equal to the distance between the black hole and the satellite. Now I want to simplify. If I have any factors on both sides of the equation, I can, well, let's take a look at this. I can divide both sides by the mass of the satellite, and it goes away. I can multiply both sides by one of these distances here, and so it gets rid of that term and gets rid of one of those terms. And so that formula then simplifies into this right here. And so I'm just left with the universal gravitational constant, or gravitational constant, mass of the black hole, the distance between the black hole and the satellite, and the speed of the satellite. Now, ultimately, that's basically any orbiting object. That's the basics of the math right there. I'm going to take it one step further. We're going to bring in the fact that the speed of light is constant, which is a semi-classical notation. Some people throw it into modern physics. Some people want to say it's classical theory. But speed of light being constant, and so that's going to be the maximum speed. If the object is massless, it'll be going that speed. If it has mass, it's going to be going under that. But we're going to use that as a limit. Speed of light is a limit, and so therefore we're going to be just using c to represent speed of light, which is a pretty standard. If you've heard the formula E equals mc squared, that c is the speed of light. And so all I've done is just made the substitution. The speed of the satellite, I'm assuming it's at its maximum. And if it has mass, again, it's not going anywhere near that fast, but we assume that it's somewhere around there. Now, what I want to know is the radius. What is the smallest radius? What is the smallest this can be? And so all I'm doing is just doing a little math manipulation. It's all for RBS. Basically, I bring that up top, and I bring this down to the bottom, kind of like cross-multiplying. Officially, I multiplied both sides by the radius and divided both sides by the speed of light squared. And that gives us this equation right here, where I have the distance between the black hole and the satellite is equal to this gravitational constant times the mass of the black hole divided by the speed of light squared. Now, all that's math derivation. Let's get down to one specific thing here. If we're dealing with Earth, plugging into the semi-classical derivation right here, I got my universal constant times the mass of the Earth. These are in SI units right here. So that's in kilograms. This is, I have to think each time, Newton meter squared per kilogram squared, and this is in meters per second, but then I square it because it's c squared. And I end up with 4.438 times 10 to the negative third, or, a little bit less than a half a centimeter. So if the Earth shrunk down, so I think in another video I mentioned ping pong balls, so it's smaller than that. So that's a semi-classical derivation that if the Earth shrunk down to within 4.4 millimeters, so something tiny, and yep, I don't have a ruler, easy access to a ruler here. Oh, nope, there it is. So 4.4 millimeters. So basically the distance between my fingernails right there from my point of view, they're shrunk down to less than that size, it would create a black hole. Now, if you actually go to Wikipedia or some page and you start looking through that, you'll see there's an extra factor of 2 in there. So that's why this is a semi-classical. This gives you, just multiply by 2 to get the Schwarzschild radius. I think that extra 2 comes in there. I'm not 100% sure on that derivation. I think the extra 2 comes into the fact that it deals with a slowly rotating body, or it could be the fact that we are actually dealing with things with mass and not light. But I don't think that second one is it. Not 100% sure where the 2 is. But if you ever go through this derivation, just multiply by 2, you have a Schwarzschild radius, and people will think you're just brilliant. So that is just one example. That's how you derive sort of the radius of a black hole and how big the Earth needs to be. So tiny little amount, about like that. If they're shrunk down, same mass, different size, it would be incredibly dense. And the sun is, I think, about 2 miles across. You can go through the derivation yourself. Hope you're having fun, and as always, rejoice, because this is physics.